Hello class, this is a continuation of the first example that we've done on sketching the function. In this example we've finished the first step, second, third, fourth, and fifth. Here are all the steps that we've done. We're yet to find any points of inflection and sketching and bringing it all together. In the last video we found that these 2 points are minimum, which means that this point here must be a maximum. All right, so we can kind of see the function already taking shape. It's going to be somewhat like this, so it's decreasing at a point. Let's try again. It's decreasing to the minimum, increasing to a maximum, decreasing again, and then going back up. Okay, so now for this next point, we need points of inflection, or inflection points. Using my next heading, points of inflection. For this, we need the second derivative. We've done this right at the beginning of our question. And now let's utilize it to solve for points of inflection. To find points of inflection, what we need to do is let this equal 0 and solve for x at this point. So for this, I'm going to divide out by 4, 3x squared minus 20 equals 0. Dividing both sides by 4. And then solving for x. Taking the square root of both sides, take plus and minus square root of 20, which is 2 root 5, over square root of 3. We require to find the y value of each, so let's substitute this back into our original function. Whoops, not duplicate, copy. Let's find the y values for each. Let's substitute first negative 2 root 5 on root 3. So substituting it in, we'll get f of negative 2 root 5 on root 3. So negative 2 root 5 on root 3 all squared minus 40 times negative 2 root 5 on root 3 squared plus 144. It's going to be negative 78.2. Let's do this. Nope, can't make it into a decimal. That's fine. This is going to be approximately negative 78.2. Now, because of the nature of the function being symmetrical, if we were to take the positive version of this, it will have the exact same y values. But just to test it out, we'll make those positive, and that one positive as well. Whoops, what's going on? Oh, that's 12. Positive 2. Positive 2. Yep, there we are. So negative, same thing, negative 78.2. So our 2 points of inflection are at negative 2 root 5 on root 3, negative 78.2, and positive 2 root 5 on 3, root 3, and negative 78.2. Putting all of this together for our sketch now. So all the points that we require, I will highlight. Let's highlight this point, this one. We need our max and min, and our x-intercepts. Putting it all together, we get -6, -2, +2, and +6. Our first minimum is at -2√5, which is about halfway between the two, approximately, and very low, like so. And this point here is also symmetrical, so it will be the exact same y value. We also have a y-intercept at +144, which is about over there. Sketching it all together. It all comes together nice and neatly. Whoops. And there we have it. Putting all the critical points in, this is -6, -2, 2, +6. This point here is at -2√5, -256, -2√5, -256. This point is at +2√5, -256, and we have points of inflection at these two here. -2√5 on √3. Let's test what that is in terms of x. -2√5 on √3, -2.5. So it's very close to our intercept. It's approximately over here and here. So those two are our points of inflection. So that those points are -2√5 on √3 and -78.2. That one, and this point here is 2√5 on √3, -78.2. So this is a rather difficult function to sketch, but I hope in doing so we are able to see all the steps required in order to solve a question such as this. Hope that gave you an insight into sketching functions using a derivative. Hope to see you in the next video. Best of luck.